All right, so before we start with new material, I just want to go back for a second and talk about the rate law, drawing thing, and just show why the math works. So last time we were talking about if we pick like trial 1 and 2, for instance, we look and see there's no change in the NO concentration. So any change in this rate has to be due to the change in the concentration of hydrogen. So when we double the concentration of hydrogen from trial 1 to 2, we see that the rate of reaction doubles as well. So we know hydrogen is going to be a first order reactant. But the reason this is going to work is because if we take the rate law for any of these reactions, we're going to have rate is equal to K, concentration of A raised to the xth power, and then the same thing for B raised to the yth power. And with it, we can just say NO is going to be A, hydrogen will be B. We can then take this and sort of form a ratio with any of these trials. So if I say this is going to be trial 2, so rate of 2, we can put it over the rate law for that first reaction. It's getting kind of messy, but and the rate law is going to look pretty much the exact same. We'll just have rate 1 on the left-hand side so we can differentiate between the two. There we go. And then if we think about what we would actually plug in here, in the last video, we actually went through and solved for what K is. But at this point, even if we don't have that information, this K is going to be the same for both of these reactions, assuming that are at the same temperature. So the K value, that constant, is going to cancel. And then if we pick trials 2 and 1, we look and see the NO concentration doesn't change at all. So even without knowing what X is, that X is going to be the same in both reactions. And if the concentration of A is the same, that whole term is going to cancel. So that's why when we just have a difference in the concentration of B, any change in that concentration is going to be responsible for the change in the rate. And we could have done the same thing with trial 2 and 3, or 1 and 3 rather, because in that case we have hydrogen staying the same, and then the NO concentration doubles, and we see the rate of that one quadruples. So the NO concentration would be second order. So we'd have a third reaction overall. But I just wanted to go through and actually show how we can kind of set those up rather than just sort of looking at the table itself. But then with the next section, we can look at the integrated rate laws. And what these are going to allow us to do is basically determine the concentration at a certain time. If we know the rate constant, we know how much time has actually passed. Or if we know the initial concentration, we know the concentration at a given time. We can solve for what that rate constant is going to be. So when we're looking at this equation here, this is going to be for a first order reaction. So where if we double the concentration of A, we see the reaction rate is going to double as well. But what we're going to have here is the natural log of the concentration at some time. So T is just going to be whatever time we're interested in. And then on the bottom, A naught or A0 is going to be that initial concentration. And then on the right-hand side, we just have the negative rate constant times however much time has actually passed. And with this equation, we can take it and rearrange it a bit. So remember with logarithms, can't speak. Whenever we have a division there, it's really the same thing as doing the subtraction between those two. So we can split this into the natural log of the concentration at some time minus the natural log of that initial concentration. And then if we rearrange it further, just add natural log of that initial concentration on both sides. We can essentially get an equation that's equal to the general equation we have for just a line. So y is equal to mx plus b. And when we look at that, this is then going to tell us on the y-axis, we're going to have the natural log of concentration. And then on the x-axis, we're just going to have the time there. So what that means, the rate constant is going to represent the slope of these reactions. So if we look at something like the interconversion of methyl isonitrile to acetonitrile. You can see we're just basically switching the carbon and the nitrogen around. This is going to be a first order reaction. So if we look at the concentration, in this case, we're representing it with pressure, but it's going to be equal to the concentration, assuming that the volume is going to be constant. But with the graph here, since it's just pressure, just regular pressure, we're going to see that this graph is going to have, for a first order reaction, going to have a curve to it. And again, on the x-axis, we've got time. Y is going to be concentration, or pressure is the equivalent to the concentration in this case, or represents the concentration, I should say. We're going to have a curve to it, but then when we change that y-axis and make it the natural log, that's going to be where we see the straight line. So this is going to be one way we could test to see what order a reaction is. If we take those concentration or pressure units and take the natural log of them versus time, if we then wind up with a straight line, that's going to represent a first order reaction. We're going to see there's other ways to test to see if it's going to be second or zeroth order as well. But with it, we've got the negative slope here because this line has a negative slope to it. So that's why we take the negative of it, just to doubly negate it, basically, get that positive number for the actual rate here. So the reaction we're looking at, 5.1 times 10 to the negative fifth per second. And then the exact unit here is going to be dependent on what unit we have on the x-axis. So if we had days, we'd have inverse days for the rate constant, or years, inverse years, but that's going to be what determines what we actually have for that unit. So if we look at a question with a first order reaction, we've got the decomposition of some insecticide in water. That's going to follow a first order decay. So a lot of the times with first order, one thing that gets talked about is nuclear decay. So those radioactive isotopes breaking down. But we see a similar thing with the decomposition of a lot of the chemicals in the environment. At least initially, they follow a first order kinetic. And with this hypothetical question, we're just thinking about some insecticide in water. We know the rate constant. And again, with those rate constants, they're going to be specific for a given temperature. So that's why with this question, we're going to be assuming that the temperature of the lake is going to be matching up with that rate constant. Otherwise, we wouldn't have enough information to actually do this question. But we know the initial concentration on June 1st, and we want to first determine what the concentration is going to be the following June 1st, so after 1 year has passed. And then we also want to see how long it's going to take for that concentration to drop to 3.0 times 10 to the negative second grams per cubic centimeter. And with this, if you wind up working in some sort of environmental field, you could be doing similar calculations to this. May not be for a year time. But if you know, for instance, when you spray a pesticide, how fast that pesticide is going to break down, you could then figure out when it's going to be at a certain concentration where it may be safe for people to then re-enter that field. Or if you have a certain time interval that you need to wait for, you can see what the concentration is going to be at that time as well, similar to the first question. But when we're setting these ones up, we're going to be using that integrated first order rate law. So ln, for the second piece here, we could rearrange it just to its initial form. But for the first one, since we're going to be solving for the concentration at that given time, we're going to want to have it in the y is equal to mx plus b form. So on the right-hand side, we know the rate constant, 1.45 inverse years. And then since we're having 1 year pass, going June 1st to June 1st, we're just going to have 1 year as that time unit. And then with these, the big thing is just making sure that these match up. So since the time, or the rate constant is in inverse years, we needed the time to be in years. We also could have been told the rate constant in inverse days. In that case, we would just want to plug in 365 days. So we just need to make sure that these match up. And then with the initial concentration, just plugging that in as the natural log. And what we're going to see is the natural log of the concentration after that 1 year is going to be equal to negative 15.96. So in order to get this just to that concentration unit, we just need to raise both sides to to E. So we'll have E to the natural log of the initial concentration. E and the natural log essentially just cancel, and then E to the negative 15.96, going to give us, that is not the correct number. So I wrote the initial concentration again, so let me, oops, it should have, where did that go? Number. Yeah. So with it, you should get 1.2 times 10 to the negative seventh grams per cubic centimeter, or grams per milliliter. Remember, milliliter and cubic centimeter are the same. So it doesn't actually matter which one you have there. And with it, the second one, again, we're going to be doing a similar thing, but in this case, we're solving for the amount of time that's going to pass. So it's going to be easier just to have it set up like this. So we can just do 3 times 10 to the negative seventh over 5 times 10 to the negative seventh, really just give us the natural log of 0.6. And then we'll be able to divide that by 1.45, negative 1.45. And we're going to see just over 1/3 of a year is going to pass in order for the concentration to drop from 5 times 10 to the negative seventh grams per cubic centimeter down to 3 times 10 to the negative seventh. All right. And then if you want to go through and practice with this one as well, it's going to be a similar type of question, but if you want to give yourself a chance to go through it on your own, definitely just pause the video, because I'm going to start going through this one. All right, so this one is similar. We're going to be looking at the decomposition of dimethyl ether at 510 degrees C, and it's a first order reaction with a rate constant given to us, and then we're told the initial pressure of the dimethyl ether is 135 torr. What is the partial pressure after 1420 seconds? So when we go to set it up, what we'll have is so we'll have the natural log. Since we're looking at pressure, we can just do the natural log of pressure at some time, and we'll have that equal to negative, and then the rate constant, so 6.8 times 10 to the negative fourth inverse seconds. And then with the time, we have that matching up with seconds already. So if they told us some amount of minutes rather than seconds, we'd have to do a little bit of a conversion. But since we've got inverse seconds and seconds, that'll just work out. And then we've got the natural log of the initial concentration, or the initial pressure in this case, I should say, which is going to be 135 torr. So when we go through, we'll get the natural log of that partial pressure at time t is going to be equal to just under 4, so 3.94. And then when we take both of these sides and raise them to the power of e, or I guess if we do e like that, so e to the natural log of that partial pressure at time t is equal to e to the 3.94. We're going to see that the partial pressure at that time, so pt, is going to be equal to just a little bit over 51. So 51.4. And then since our pressure unit was torr to start, that'll be what we have for the pressure. So again, we can use the pressure as a substitution for the concentration of these gases, because the pressure is going to be equivalent to the moles. And as long as the volume is constant, they'll be representing the same thing essentially. All right, and then so that was with the first order reactions, where if we see a doubling of the concentration, we're going to see a doubling of the rate as well. So with the second order, what we'll see is if the concentration doubles, we're going to see the rate quadruple. And we can do something similar where we've got an integrated rate law, so we can see the relationship between time and concentration, provided we have the rate constant and the initial concentration. So again, we can have a a form of this equation is equal to the y is equal to mx plus b. So again, the slope of the line is going to be equal to the rate constant. And in this case, we'll just have a positive slope, so we don't even have the negative sign here. But rather than having the natural log of these concentrations, we're going to have the inverse of the concentration. So we've got 1 over concentration at some time on the left, and then 1 over the concentration, or the initial concentration on the right-hand side. So when we look at the graph, like I said, the slope is going to be equal to that rate constant. And with these second order ones, the slope is going to be positive, because on the y-axis, we're going to have the inverse of that concentration. So we'll have 1 over concentration of A, or whatever that substance is actually going to be. And if we think about the decomposition of NO2, so at 300 degrees, we're going to have it break down to just NO and then elemental oxygen. And we can see on the left, or the right here, we've got some table of time versus the concentration of that NO2. So we can see as time goes on, more and more of it's decomposed, so that the concentration is going to decrease. And if we take that concentration versus time, we're going to see a pretty steep line. And then if we again take the natural log of that concentration, because this is going to be a second order process, we're still going to have a little bit of a curve to it. So if this was a first order reaction, we'd have that straight line like we saw with the previous examples. But now that this is a second order process, when we check with the natural log versus time, we're going to see a slight curve to it, which means that this is not going to be a first order process. But then if we take these concentrations and do the inverse, now we're going to see that positive slope of the straight line. So this is how we can check to see if a reaction is going to be second order. If we do the inverse concentration versus time and then get a straight line, that's going to represent a second order process then. Yeah, so if you look at it here, with the changing concentration, or the changing the inverse concentration from 0 to 50 goes up by 27, from 50 to 100 goes up by 27. And then from 100 to 200, we've doubled the amount of time. So now we see it go up 54. So now we're seeing that straight line, because this is going to be a second order process with these inverse concentrations. So if we look at a question with it, so the decomposition of hydroiodic acid or hydrogen iodide in the gas form into elemental hydrogen and iodide, going to be a second order process. So that's why if we look at the rate law, K is equal to that concentration squared. So since we've got an exponent of 2 and we don't have any other reactants with it, that means this reaction is going to be second order. So if we double the concentration of this hydrogen iodide, we're going to see it's going to decompose at twice the rate, or quadruple the rate rather, because it's a second order process. But in this case, we're told the rate constant at the given temperature. And we want to figure out how much of that substance is going to be left after 10 minutes. If we start with an initial concentration of 0.010 molar, so just remember mole per liter is really just molar. So that's why when we look at the unit here, it's really inverse molar, inverse minute as well, because we've just got molarity flipped. But now if we want to solve for this equation, it's going to be pretty much the same thing we did for the last one, but instead of the natural log, we're going to have the inverse concentration. So you can see the general form of the equation up here. But when we actually plug in our values for this question, the rate constant, 30 inverse molar inverse minutes, times the amount of time that's past 10 minutes. So again, we want to make sure the time units match up there so that these minutes just wind up canceling. And then we've got an inverse of the initial concentration, so 1 over 0.01. So this is going to give us 300 plus 100. So we really got the inverse of that concentration at time t is equal to 400. So when we isolate that concentration, what we're going to get is a molarity of 0.0025. Again, we can see it's decreased because we started at 0.01, and then after 10 minutes, we've got we've got 25% of that left essentially. And then regardless of what type of reaction we're looking at, so whether it's first order, second order, we'll still see zeroth order in a second. But regardless of what type of reaction we're looking at, the half-life is going to be defined as the amount of time required for the concentration to become 50% of what it was. So if you look at the equation here, concentration at time t is going to be equal to 0.5 times that initial concentration, because this is just saying on the right-hand side, we're going to have half of what we started with. And it's going to be what the concentration is at the half-life. It's going to be 50% of that initial. And if we look at the graph to the left, we've got the pressure, which again can be a substitute for the concentration versus time. And with this one, what we're going to see is after maybe 1200 or 1300 seconds, the pressure decreases by half, so 150 to 75. That's going to be one half-life. And then since this is going to be a first order process, we'll see exactly why this is. But since this is going to be a first order process, what we're going to see is that second half-life is going to be the same amount of time. So still 1200 or 1300 seconds, whatever it's going to be approximately. But in this case, since we only had 75 torr left, the amount lost is still only going to be half. So in this case, we're only going to lose 37.5 rather than 75, just because we've got less to begin with when we get to this half-life. But the amount of time is going to be the same, and that's going to be characteristic of a first order process. The half-lives are always going to be the same, but with each subsequent half-life, we're going to see that we're going to lose a little bit less. We're going to lose 50% as much as the previous one, basically. And with this, we can take that integrated rate law and essentially substitute in half of that initial concentration. So instead of concentration at some time, if we're interested in the half-life, we know that concentration at the half-life is going to be half of what we initially had. So we can just plug that into the place of AT. And that's why on the right-hand side here, we've got T with the 1/2 subscript, because that's representing the time needed to get to that half-life. But when we look at this, the concentration at the initial concentration is going to be the same on the top and the bottom here. So that's really why we just wind up with the natural log of 0.5 on the left. And now this is just some number. We don't have a variable in there. So natural log of 0.5 is always going to be negative 0.693. So we can continue to go through this one, isolate the time, and we're just going to wind up with the time needed to get to that half-life for a first order process is going to be the 0.693 divided by whatever the rate constant is for that particular reaction. And then with the second order one, we can do something similar. In this case, though, again, we've got the inverse of concentration. So on the left-hand side, that's why we've got 0.5 times the concentration on the bottom here rather than the natural log, because the integrated rate law itself is just going to be a little different. But when we go through and kind of continue to rearrange this one to solve for the half-life time itself, the reason we've got a 2 here now is because 1/2 is really the same thing as 2/1. So it just makes it a little bit easier than having a fraction in the denominator or a decimal in the denominator. And then we've got the same thing in the denominator here. So we can just do 2 minus 1. And 2 minus 1 over the initial concentration is the same thing as 1 over that initial concentration. So just note with this line down here, this third one, now we've got 2 equal signs rather than the plus sign here. So we've just got a little bit of a different sort of format here. But now this is saying the inverse of that initial concentration is just going to be equal to the rate constant divided by or multiplied by the time. And again, we're isolating the time for the half-life, so we can divide by that rate constant. And we'll see for a second order process, if we need to determine how long the half-life is going to be, it's going to be the inverse of that rate constant times the initial concentration. And then with 0th order reactions, what we're going to see is that with the 0th order, our rate law is just going to be rate is equal to K. So the concentration and the rate constant are going to be independent of each other. So when we look at the graph, that's going to be a straight line for a 0th order reaction. What we're going to see is that it's just going to be the concentration versus time. And again, we'll have a negative slope. But with this one, it's just going to be concentration versus time, and we'll have a straight line. So the rate constant or the negative rate constant will be the slope there. And then when we're looking at the 0th order, if we again do the same thing, So for the half-life, if we do 0.5 is equal to the initial one, rather than having the AT here, what we're going to see is we'll subtract the initial concentration from both sides. We'll really wind up with negative there because we're subtracting a full from the right. We've got to subtract a full from the left. So now we're going to have negative half of the initial concentration. And then we'll divide by negative K. Really just makes it plus. So with the half-life here, we could have 0.5 times the initial concentration, or another way of saying that would be the initial concentration over 2. But that's going to be how we can solve for the half-life of a zeroth order reaction. And again, with these ones, even if we don't remember what these equations are for the half-life, if we've got the integrated rate law, we can always just change the concentration at time t to 0.5, the initial concentration, and then kind of just go through that rearrangement to isolate the half-life time by itself, like we have for all 3 of these. And then that seems like a good spot just to